Welcome everyone in Aquabiotech. The aim of this workshop is today to provide you a kind of summary of 5 years of work in the EnviGuard project, and give you also an overview what's happening, what's going on in the field of the marine monitoring systems, and how these new developments can help the development of the whole blue growth industry. I would like to ask Mr. Franco Scamri to have his first speech about the importance of the blue growth and the maritime industries, and how these areas should be in line with the environmental sustainability.
Can I close it?
Yeah.
Good morning. Thank you, Aquabiotech, for the invitation. There is no doubt that one of Malta's main economic goals is to aim for blue growth and job creation. Blue growth consists in the long-term strategy aiming to exploit the maritime sectors. Undoubtedly, the maritime sector comprises important potential for economic growth and innovation. It is the maritime contribution to achieving the goals of the European 2020 strategy for smart, sustainable, and inclusive growth. Malta has a long tradition in the maritime industry and has been on the forefront for a number of international maritime fora. Malta is strategically located in the center of the Mediterranean Sea, 93 kilometers to the south of Sicily and 290 kilometers to the north of Africa, at the crossroads of southern Europe, North Africa, and the Middle East. Malta's geographic position placed the island at the forefront in the maritime sphere. Throughout centuries, rulers of Malta recognized the importance of the maritime sector and its effectiveness to link Malta to our European counterparts. The Mediterranean Sea is strategically located and geographically situated at the interface of 3 main continents, namely Europe, Africa, and Asia. The Mediterranean Sea has always been a hub for culture and trade between its neighboring countries and beyond. The seas and oceans can certainly be a source of jobs and prosperity, but only if they are healthy, safe, and sustainably managed. To drive forward key maritime sectors like renewable energy, aquaculture, tourism, and blue biotech, we need to improve ocean knowledge, planning, and security, and improve cooperation and collaboration among maritime stakeholders. The Mediterranean region offers the potential for further economic growth in the maritime sector. The region is renowned for its active ports and attracts numerous tourists due to its cultural heritage. Moreover, the basin is notorious for its biodiversity and numerous marine protected areas. It is recognized that good governance needs to be enhanced in order to address issues such as climate change and environmental protection. Research clearly indicates that the blue economy offers lucrative business opportunities, particularly if the culture of innovation is embraced, leading to blue jobs creation. Having said that, it is evidently clear that the region is also experiencing important skills gaps. Many maritime industries are lacking people with the right qualifications, skills, and experiences. Consequently, it is crucially important that employers, public authorities, and unions join forces to design effective solutions to this situation if we truly want to benefit from the opportunities that the ocean offers us. All maritime stakeholders need to think holistically and outside the box. It is imperative that we realize that the blue economy will grow if our seas are healthy and secure. Our seas are rich and often underestimated source of innovation, growth, and employment. They provide valuable ecosystem services and resources on which all maritime activities depend. Since its creation in 2007, the Integrated Maritime Policy has sought to enhance the sustainable development of the European maritime economy and to better protect the maritime environment by facilitating the cooperation of maritime players across sectors and borders. The IMP sets out a coherent strategy to enhance the sustainable development of maritime sectors. Coordination is necessary to manage the increasing impact of maritime activities on each other and on the environment, to ensure the safety and security of European citizens and to maintain a qualified workforce. Enhancing knowledge exchange and sharing, particularly between Mediterranean countries, can play a vital role for the blue growth and is key to strategic objectives of the Union under the Integrated Maritime Policy. Exchange of information is also vital for maritime security strategy. Ensuring the security of the European seas can play a crucial role to enhance blue growth. Strengthening the security of seas and oceans is also an essential part of the blue growth agenda to create growth and jobs in the maritime economy. The aim is to increase the efficiency, quality, responsiveness, and coordination of surveillance operations in the European maritime domain and to promote innovation for the prosperity and security of the EU and its citizens. Data from the marine environment is undoubtedly a valuable asset. Unfortunately, marine data collection, storage, and access in Europe has been carried out in a fragmented way for many years. Most data collection has focused on meeting the needs of a single purpose by a wide range of private and public organizations, often in isolation from each other. Rapid access to reliable and accurate information is vital in addressing threats to the marine environment, in the development of policies and legislation to protect vulnerable areas of our coasts and oceans, in understanding trends and in forecasting future changes. Likewise, better quality, more easily accessible marine data is a prerequisite for further sustainable economic development, in accordance with good environment entrepreneurs are those who think outside the box and are astute enough to identify and capture market trends. Scientific research shows that the seas offer a variety of economic opportunities, which to date have not been exploited as much as they deserve. It is time for entrepreneurs to realize the importance of scientific research to business activities. Scientific research should not be regarded as a cost and time-consuming exercise, but an investment which could yield important profits. On the other hand, it is imperative that academics adopt an approach of pro-business culture. Academics need to avoid falling prey to marketing myopia. In simpler terms, they should focus their efforts and researches on fulfilling market needs. Consequently, it is imperative that we build bridges between two social groups for their own success and the economy at large. Now I am going to share with you what we are actually trying to do in Malta with respect to cluster development. The agency launched its first working group on logistics, which is one of the economic pillars of the National Integrated Maritime Policy, in January this year. Logistics is part of the Integrated Maritime Policy that will provide vision and direction so that the profile of Malta as a maritime center is actually raised. Malta Marittima Agency has identified maritime logistics as one of the important clusters for development, contributing positively towards the economy and providing jobs. Stakeholders from 15 different entities within both the public and the private sectors form part of this working group and actively participate and provide their inputs during the meetings. Maritime logistics is a specialized field, not only consists of maritime shipping and transportation, but includes shipping management, port management, operations management, the logistics and supply chain management, shipbroking, ship handling, maritime and marine engineering, etc., etc. Thus, the aim of the logistic cluster is to support and strengthen the sector as necessary. This would ensure an integrated approach and that all relevant stakeholders have the opportunity to participate and voice their opinion, while sharing of experiences and cooperation while identify opportunities. The biotechnology and biopharma sectors clusters are still in their infancy and would indeed require a highly skilled workforce to tap into the opportunities that such sectors would provide. Because they are rather vast and dynamic sectors, Malta Maritime Agency shall be identifying the main priority areas in order to come up with the adequate instruments to sustainably explore and exploit such sectors. Though the setting up of Maritime Cluster Working Group dedicated specifically for biotechnology, the agency will be seeking to strengthen the relationship among the private sector and scientific researchers. As a result, Malta Marittima will be in a better position to provide the ideal policy framework leading to further growth and development. Thank you.
Thank you, Franco. If you have any questions to Franco. Do we have any questions through the web stream? No? Okay. So thank you very much for your speech. And we can go forward. Claudia, could you ask Ines to come? Because she should join us. No, I have some. Okay. That's why I don't have the. Okay. So I would like to give you an overview of the project, of the EnviGuard project, which started in 2013 in December and ending now in 2018, end of November. It was a 5 years project. The project leader was a German company and institute. It's called TTZ Bremerhaven, and Mr. Björn Sokov was the coordinator of the project, and he was my co-author in developing this presentation. Aquabiotech was one of the partners in the project, but as you will see, we had an important role in the project. Altogether, the project had 18 partners from different European countries, and we had a quite large number of SMEs, companies in the project. We had 11 SMEs in the project. because the original idea of the project was to produce a final product at the end of the project, which can be directly used by aquaculture farms. What should I do now? Later. Which can be used by aquaculture farms, environmental authorities, or any stakeholders which is interested in the maritime monitoring. As I said, it was a 5 years project, 60-month project, and the total budget of the project was 7.2 million euro. But this is the budget with the own contribution of the partners, because it was a 7 framework program project, and in that framework program, not all the partners had 100% funding in the project. So, for example, Aquabiotech also invested around 20% of our budget in the project. The project had 3 core ideas, 3 core goals, what we wanted to achieve. To develop 3 biosensors to detect algae, especially harmful algae in the marine environment, to detect chemicals in the marine environment, and also viruses and bacteria in the marine waters. I don't tell too much about the sensors because Ines will have a presentation about the whole issue, what sensors has been developed in the project. Just summarize the main ideas. In the case of the algae detection unit, the idea was to use a quantitative nucleic acids based detection method, especially for the toxic algae, as I said. The pathogen unit was focusing to develop something to detect Escherichia coli and especially beta nodal viruses. Or the virus what we wanted to identify was the VNN virus, which is a specific disease of the Mediterranean fish. It's especially dangerous for the sea bass, but it can also infect the sea bream. But this is the most limiting factor of the sea bass production in the Mediterranean area. So it was especially important for us to develop a detection unit for this. And for the chemical contaminants, we focus on the PCBs. The plan was to focus on the PCBs, the ocydecasic, and the saxitoxin to detect. But the saxitoxin was not very successful at the end. Maybe Ines will talk more about this. As usual in the EU projects, the original goals of the projects, the main goals were achieved. But some of the goals we could not achieve. We tried to do mitigation measures within the projects to change the work. But sometimes we failed because it's a research and you cannot say at the beginning what will be successful and what not. And the idea of the project was that, and we implemented this as well, that all the different sensors will provide their data to a common platform, and this platform will store the data from where the different stakeholders can access to the data. And this is what Franco also mentioned. It's very much in line with the recent strategies and policies that the data collected by different systems and fragmented systems should be collected on the same platforms to provide a kind of data hub for the end users and stakeholders. And the idea is that this whole system can work as a kind of early warning system for the different stakeholders, especially for the aquaculture producers, and they can take the necessary measures if, for example, toxic algae bloom is expected according to the signals of the different sensors. And this is what we have at the end of the project. This is the prototype of the project, which is still too big, we have to say. So to achieve the original goal of the project, we have to further develop this, because okay, this can be put in the sea, but it's still too big and too expensive to be autonomously operatable on the product development work of the partner has to continue after the project as well. Just a second. Okay, and you can see the main. You can for more information about the project, you can visit you can contact the project leader, because they are the official information provider of the project. But we also have a website for the project. What I don't see, maybe I forget it, but maybe we'll have it on another slide. It's called EnviGuard.eu. Okay, and in my next presentation, let me give you an overview about one of the first tasks of the Aquabiotech, what we did. One of the first work package of the project was to survey the needs of the. Oh, sorry, something wrong with here. Yeah, okay. Was to survey the needs of the market, what the stakeholders and especially the fish farmers expect from a monitoring system, and what are their needs for the monitoring systems. So we launched a market survey, what was coordinated by the Aquabiotech, to survey what the aquaculture, how large is the aquaculture market for this type of system. First, we investigated the different part of the aquaculture. On this slide, you can see the main form of the aquaculture, which provides the majority of the world aquaculture production. And we identified that the biggest interest for a new monitoring system can come from the marine cage aquaculture, which is really impacted by the environmental conditions. And the extractive aquaculture, the mollusk production, can be also very important, because they suffer the most from the harmful algae, for example. And what is sure, that this market is growing, because the aquaculture is one of the fastest growing food production industry of the world. On this first slide, you can see the comparison of the world fishery and aquaculture production for food. And you can see that while aquaculture is continuously growing, the fishery, the capture fishery, is stagnating, and we can see it's decreasing according to the trend. So it's expected that the fish product needs of Europe will be covered from aquaculture in the future. And if we can have a look on the other figure, we can see the share of different aquaculture production systems from this world aquaculture production. So this is mirrored here. This bars shows the seaweed production, which could be also interesting for the monitoring systems, but the majority of the seaweed aquaculture happens in Asia, not in Europe, and we wanted to develop a product which is more interesting for Europe. The other big parts of the aquaculture which can be interesting, that the majority of the aquaculture production, these light blue bars, comes from the inland aquaculture, from the freshwater aquaculture, also mainly from Asia. What was important for us, this red bar, which is the marine aquaculture, marine fish aquaculture, marine and coastal fish aquaculture, which mainly happens in Europe. The main species, the main aquaculture types in Europe are the northern aquaculture of the salmon production and the southern aquaculture of the Mediterranean fishes like sea bass and sea bream here in Malta and Greece and Turkey. And another big industry is the dark blue bar, the mollusk aquaculture, which is also a potential market for this type of product. We, at the beginning of the survey, we planned a kind of online questionnaire type of survey, but soon we have to face with that this does not work anymore. People don't like to fill up questionnaires online, so it's a lesson for a future projects. If we plan any kind of survey, it should not be based just on online survey. And after a few months, we realized that we cannot have answers from, for example, the northern mollusk aquaculture for our questionnaire. However, the questionnaire was prepared in cooperation with aquaculture farmers, what is interesting for them, but we could not have answers. So we decided to change a little bit on the method, and together with the Turkish partners, we followed the method that the Turkish partners visited aquaculture farms in Turkey. They have the questionnaire with them and prepared a kind of structured interview with the farmers and filled up together the online form. We did something similar with the Greek farmers. We have a Greek colleague who was a very big help for us in this because he could contact the farmers on their language. And we called farmers, we did phone interviews with the farmers and filled up the questionnaires based on this one. And we wanted to cover at least the Mediterranean aquaculture, because that's for us this was the most important part and the most important possible market. And to have this survey in Greece and Turkey gives a good results about the Mediterranean fish aquaculture, because these two countries covers the 72% of the whole aquaculture production in the Mediterranean. And finally, we got answers from 35 Greek farmers, and our Turkish colleagues visited 19 fish farms in Turkey. Some of the results, not all the results of the survey, but some of the interesting results what we had, that the majority of the answers came from farms who do growth activities, so they produce fish for the market. So the answers are relevant for us, and most of them were cage farmers. However, we had a few answers from shellfish farms as well. What was interesting that asking them what are the main threats on their farming activity, and the virus and the parasites, viral diseases and the parasite diseases were the most important things what they would like to detect somehow before a disease outbreaks in their systems. It was also interesting the answers relating the algal blooms. How can they tackle these problems? And the result shows that they expect new technologies will help them to fight against these problems. But at the moment, they don't have any developed system to detect these problems and serve as a kind of early warning mechanism, because they just notice the diseases or algal blooms based on the fish mortality and visual changes in the species in the behavior of the fish. A few of them do water quality monitoring, but this cannot give them enough data, enough detailed data, what type of disease or algae bloom is expected in their area. And these are the results of the questions. What type of technology do they expect in the near future? And what type of technology could they use? And the most important thing what they mentioned all the time was to need something, some kind of technology against the diseases and pathogens, and that was a signal for us that we have to focus, for example, on this VNM virus detection. It was interesting that environmental pollution was also important for them, so this shows well that why we developed the sensor for the chemical pollutants as well. Of course, the algal blooms in the Mediterranean region was not so important. If we would have done this survey amongst the northern aquaculture farmers, especially mussels farmers, algal blooms would have been the most important, I think, for them. So these are the main results of the survey. Thank you for your attention. If you have any question, I can answer.
There are a few, but maybe it's a bit early. Do we have one answer here?
So?
Did you share? Okay.
Okay, so I would give the floor to Ines to talk about more detailed results of the project. Number 3, I guess.
Yes. I'm sorry, I have to get my notes. I forgot them in the chair. So good morning. Following Tamas' first presentation, I'm going to speak to you a little bit about the sensors that were developed within the project. So the main objective of the EnviGuard project was to develop a prototype. This prototype would have several sensors, and the sensors would be cost effective. They would have a clear advantage over the market. They would save a lot of money when it comes to European analytical research industry, because as you know, current standards for measuring these kind of specific endpoints are very expensive. And they would be able to save display and send in real-time data to the end user. So we would have a online platform where we would be able to access the data that it's being measured in the field. So the biosensors are supposed to be used as single portable devices, or as in a whole, as in all the 3 sensors together, but they would actually be able to be used individually. They will also be able to send real-time information for a period of a week without maintenance. The biosensors will also be developed to go beyond the current state of art, like I said before, so they will be reliable and simple in operation. They would combine nanotechnology and molecular science, and they will help the European research with the use of highly innovative CMEs like Aquabiotech in the forefront of quickly developing markets. So as Thomas said before, EnviGuard developed 3 sensors. An algae one with a green symbol, a pathogen, and a chemical. So regarding the algae module. The algae module, the ADU, we call it ADU from now on. So the algae module will be able to detect and quantify species of algae that are affecting they are toxic algae, they are affecting European waters. For example, those species you can see over there. So what is the principle behind the sensor? The sensor would at some point break the cells, releasing RNA sequences, ribosomal RNA, and through Algae-specific regions, they would be able to identify the species from where these RNA is from, and the sensor is going to be able to tell us the species and the cell numbers that we are measuring at a time. So the Algae module. So how does it work? So imagine we are in a ship. The ship will take a water sample. The sample will go through the autofilm, that is a filtration unit, and then to the biosensor. So what will happen? So the autofilm will collect the sample through this container. Then that will be filtered through a filter, obviously, and then the ultrasonic equipment will break the cells, releasing the RNA particles. Then the sample, after the ultrasonic, will go directly to the ADU, and it's going to be measured by the sensor. So how does the sensor work? The sensor has a rack of chips that are able to measure, to be attached to the RNA, then will give us a signal. So they will be pushed from the stacker through the biosensor, and then when they get to the biosensors, they will be measured, and we will have an idea of the quantity of algae that we have in our sample, and later what we should do with, for example, our culture of, let's say, mussels. So some results that we obtained from the sensor. So we did some calibration curve with all of the species that were in the slide before, and we were able to obtain kind of a limit detection. So we would be able to detect per species around 50 cells per liter. This is quite good. So the chemical module. What will the chemical module be able to detect? It will be able to detect oxalic acid and main pollutants like PCBs. So why oxalic acid? So the oxalic acid is a chemical that is produced by toxic algae that are currently in European waters, and these microalgae will be ingested by molluscules. So we eat molluscules. So of course, if we are eating something that has a chemical, we will get sick. So this is very important it's a very important chemical to analyze, as it's deleterious for us. So an early warning system will be super great if we can measure this chemical. The CDU is also able to, as I said, measure PCBs. So it's able to simultaneously analyze two types of chemicals, so oxalic acid and PCB. PCBs, why PCBs? PCBs are chemicals that are bioaccumulated through the food chain. So if we consume a lot, for example, of a fish that has eaten thousands and thousands and thousands of other fish contaminated with PCB, at some point this will also be to jeopardize our health. So PCBs is also a very important parameter to measure. How does the CDU module works? So the module has a sensing chip with 12 sensing cells. It's these billion squares over there, and each one of these the squares has resonant nanopillars. So this chip is going to be sealed into a chamber and then put it in the sensor. Okay. So when I mentioned before that the sensor would move, so this sensor it's going to be in a chamber inside the biosensor, and so we will add the components that we need to measure then PCBs and oxalic acids through the chamber that contains the chip, and how is this flow going in the chamber. So we have a set of peristaltic pumps that will push each one of the solutions that we are taking, so from these recipients. And from these, we will be able to measure and have a signal of, and then quantify the chemicals that we have in our samples. So we managed to obtain, after a lot of optimization of the sensor through the time, good limits of detection. So for PCBs, we were able to obtain 22 micrograms per liter, and for oxalic acid, 25 micrograms per liter. When comparing the CDU module with standard techniques, so we are able to say that it has great optimization. It works very well as a dependent sensor and as a part of the EnviGuard port. It can do multiple analytes, so PCBs and oxalic acid. It's easy to use. You don't need to do anything. You just need to press a button when it gets to measure a sample from the water. It's real time. It takes each analysis takes about 2 hours to take place. It's label free, and the only 2 things that we need to work is on the sensitivity, because when we are working with PCB especially, these compounds, to have a real indicative of the amount of chemical, the PCB that we have in the water, we need to do a filtration, and we need to concentrate the sample 1,000 times. And with the autofilm, we could only get 500, but our limit of detection is not bad. It's actually very good. So the pathogen sensor. So what is the pathogen sensor able to measure? It's able to detect and quantify, once again, in situ, like the CDU and the ADU, with a single sample, E. coli and beta-adenovirus. So what is the principle behind the process? So for E. coli, we attach to our ship material streptavidin and biotin, then the antibiotic specific for E. coli, and then we run another cycle where we had an antibiotic and a fluorophore that will give us a fluorescence that we can measure. For the virus particles is the same, so for the beta-adenovirus is the same. What changes is instead of using antibodies we use aptamers.
Can I ask a question?
Sure.
Can you go back to... So when you sample for E. coli, do you sample continuously or do you sample test and move on? So is it a flow process or do you sample, react with antibodies and whatever, whatnot? Is it a continuous process?
Okay, so when you take the sample, the PDU will start working. So through the chamber, what will start, it's going to be the solution. So there's going to be a solution that's with streptavidin that will attach to the ship, and then another solution that will attach biotin to streptavidin, and then another solution with antibiotics. Then it gets our sample, and that probably has E. coli. So when E. coli comes in, it will attach to the antibody, and then another solution comes. So it will work by peristaltic pumps. So each solution, each one of these components, it's one run, let's say.
And there's a continuous running, so it's one run and then
The reason I'm asking is I was wondering how it does get through the problem of the low density of the organism generally in the water, which could make it hazardous.
With the autofilm.
Yeah.
Because the autofilm filters, I think, if I remember correctly, it's 5 liters of water.
5 liters of water, yes.
5 liters of water altogether. It's 5 liters of
So
water.
how do you concentrate the organism?
It's concentrated with...
500 times.
Yeah.
500.
500 times.
So then,
And how long does it take?
20 minutes.
20 minutes, half an hour.
20 minutes.
Depending on...
So you concentrate how many liters? 1 liter?
5
5.
liters. And then the concentrated amount is the one that is actually run through the system that Ines just explained.
Right. And what sort of density would you expect after that 1 hour?
It depends how much is in the water.
Count, typical count.
Can I answer this question later?
All right, okay.
Yes, because at some point I will speak about the detection limits and what's going on. Yes?
We should obviously point it to that direction.
Okay. So I give you the PDU. So we will have a ship that is right here, already covered with a sealer that will go inside the chamber, and over there you have the closed chamber. So the chamber will be put in right here, like I was trying to explain before. Maybe I didn't explain myself very well. And then one of these tubes has the solutions, streptavidin, biotin, antibiotic, blah, blah, blah. And then our sample, all of these will go through in our sample as well, and then we will have a sensor below the plate that will be able to measure the amount of particles that we have in the sample. So for E. coli, we're still trying to optimize the process because we had some problems with purchasing the antibodies, and now we are trying to do the same with aptamers. We use the aptamers for the virus. In the beginning, we tried the antibodies for E. coli, but we couldn't. Now we are trying to do something with the aptamers. Okay. Did I explain myself well? Okay.
The density is the most particular thing. No? I mean, when you consider the low incidence that E. coli can have, a huge difference for head. And when you consider that it's a big ocean, it's a big water.
Yeah.
So it will all depend.
But
you can concentrate it in a short enough time, and that concentration will be. I have serious doubts here. My serious doubts is if the collection is efficient enough, or if it's accurate and does not harm the organism in the way in the process. If there might be more, I was about to say traditional manner, but more kind of some more standard scientific ways. Like, for example, if I was looking at organisms of a certain concentration, I mean, traditionally you would dye, and you check for fluorescence and check for shape.
Let me suggest to go forward with the presentation, and after that we have the discussion. Okay.
Okay. So we did some studies like Aquabiotech because, you know, there was no studies about beta-adenovirus and when this virus has effect on fish. So Aquabiotech runs some studies, and we are able to say, after our beautiful team and their work that they performed, that everyone is very proud of them. We are able to say that the minimum effective dose for beta-adenovirus is 2 up to 10 particles per milliliter. And we also have to say that the PDU needs a lot of work. We need to work on the optimization of the sensor, because right now the limit of detection that we can measure is 6.3 cells per milliliter, up to 5. So 6.3 up.
At a go, how much do you look at each go?
What do you mean?
In terms of volume.
The volume of water sample
Yeah.
that you, still 5 liters.
5
Because
liters.
that's
No,
not-
you look at 5 liters at a go. Really?
Yeah.
That's a lot.
Because we concentrated.
Yeah, okay.
So
But
in
at the end of the
we
day-
will so after the filtration we will have like 4 milliliters of solution in a
Alright,
O-ring.
That's what I'm talking about. Okay.
Yeah.
Okay.
Yes? Okay. So as conclusion, we are very happy with our prototype. It's very beautiful. It works perfectly. It needs some optimization. So quickly, this is the out-of-film. This is the ADU from our field trials in Orkney. We were able to take some samples and we have very good results. We just need to validate the procedures, and that's it. I think it's almost ready to the market, the ADU. PDU, it needs a lot of more work. It needs to be optimized. We need to also run tests with E. coli to be sure that at the end the PDU will be able to measure E. coli as well. And the chemical sensor is also working very well. We just need to work on the optimization, but we are very proud of the prototype. But still, it's still a prototype, so we cannot judge as much as we could if it was a real on the market thing. So thank you. So shoot away. Questions? Yes.
Yeah.
You've got cage in the safe. and assuming it's been put in the correct location, you've got good dispersive capacity. You can have a lot of variation in samples. So is there not sample error here? Because if you're saying you can detect it in one sample, I mean, how many samples are you actually taking?
You can take, if I'm not mistaken, 4 to 5 samples a day over a period of a week without maintenance of any of the sensors.
Right, so you can develop a time series of data?
Yes.
Okay.
Tell me.
Question. I saw one of the pictures you showed, like a nano picture, those resonant
Nanopillars.
nanopillars. So basically, the sensor, what I'm just guessing, you have an antibody that attached to other molecule, but the sensor itself works in the way of of the resonant of that layer. So you extrapolate. I mean, basically the concentration correlated to the resonant of that layer.
Yes.
Basically.
So the nanopillars itself have a certain wavelength, and when a chemical is attached to the resonant nanopillar, you would have, according to the concentration, different wavelengths.
Okay.
So you will be able to measure.
So you
the
are
quantity of
vibrating this mechanically, the wavelength of that layer.
There is a
Yep.
spectrophotometer.
Yeah, you are measuring the wavelength.
But it's mechanically moving?
It's magnetic. So it's deviation of magnetization.
Basically, that's what we're doing. That's what we're doing.
Spectrophotometer there that basically measures the difference in absorbance when it's actually
Excited by whatever light sources you have.
Yeah.
Okay. It's just a quick calculation. You said 4 mil, no?
Yes.
You're reducing 5 liter to 4 mil. Right. So, how much is what would be the not accepted level of E. coli particles in 5 liter? So we know what density would have in 5 mil. How much would that be?
Look, this is a sample from
Yeah,
the.
no, but how much would be accepted to have in 5 liter, and how much would not be acceptable?
As in the threshold for
In the ocean,
Yeah,
say.
in the ocean.
Whatever we say, right? My alarm bells are ringing.
Yeah.
What would I expect to have? in
I
5 liter?
wouldn't know. I don't know.
It depends
I
on the environment as well, and the farming type, what they have. It
But also
depends.
by the regulation of the country.
Regulations, yeah.
Yeah, because at that sort of density, you could 4 milliliter. It could be passed through a film between two substrates, yeah? And it would be fast enough. You can't pass 5 liter, but you can pass 4 milliliter.
Yeah.
And then you could use really fast methods. I mean, these days with data processing, since
But you need a lot of manpower as well.
no, this will be automatic, because
Okay.
with very fast computing, it's like we recognize faces, no? You could practically do the same thing.
May I suggest to move forward because we are getting out of time a little bit. Do we have any questions from
Science.
the web?
Not yet.
Not yet. Okay. So I think we should have a coffee break now, and in the next part we will continue with some other projects what we have here, where we work here in the Aquabiotech, and related a little bit to this EnviGuard project, and give you an overview about the whole picture. So the coffee is here, I think, and yeah, feel free to have a coffee.
I didn't know we were down to 4.
EnviGuard is an FP7 project financed by the European Union. The consortium includes 18 partners from all over Europe, bringing together the highest level of experience in the aquaculture field to respond to the need to create a reliable and cost-effective risk management tool with the coordination of TTZ Bremerhaven, Germany. The prototype, developed by the EnviGuard team, will be tested in Orkney Islands, Scotland. The prototype works as an early warning system for local and regional authorities and fish farmers to reduce the risk to economic losses and human health. The prototype can be set individually or combined with other water quality monitoring systems. The device consists of 3 different detection units: microalgae, pathogens, toxins and chemicals, which saves, displays and sends real-time data to a server and can be accessed anytime via mobile and internet. The algae detection unit helps in preventing economic loss related to toxin contamination in shellfish or toxic algae detrimental effects on fish, as well as damages on human health. The sensor module is composed by a pre-chamber with heating and an electrochemical unit. The unit transmits a measurable electrochemical signal and can be used for automated sampling of marine microbes, sample preparation and data storage. The chemical detection unit is an advantageous and unique alternative to current analytical techniques. The approach is based on a novel optical nanobiosensing unit, integrating heterogeneous technologies from different fields of science and technology. The unit uses resonant nanopillars as transducers and monoclonal antibodies as selective bioreceptors to detect toxins and man-made pollutants. The pathogen detection unit is an innovative technology for virus particles and bacteria observation in seawater. The key elements of the new sensor system are a microfluidic system utilizing detection chips with bioactivated surfaces and an optical detection unit. With this procedure, qualitative and quantitative signals can be generated, which will give clear signals to the end users. The prototype pumps the water from the seawater column and sends it to the autofilm system for filtration and submission to the ultrasound process. This method then breaks the cells and releases the RNA particles of the samples and sends it to the algae sensor. This sensor analyzes the RNAs to get the harmful algae species and cell numbers. The chemical sensor then quantifies the toxins and pollutants in the water, which can be correlated with the data provided by the algae module. The pathogen sensor detects E. coli bacteria and beta noda virus to protect fish farms from any occurring fish disease. Getting these in situ measurements from one sample is currently unique on the market. As disease events can lead to the collapse of single aquaculture operations or an entire sector at national and international level, this early warning system could be a priceless addition to disease surveillance, disease response, and quarantine programs. EnviGuard will provide a unique competitive advantage and leadership to the European aquaculture industry in biotechnology, sensor development, diagnostic technologies, and nanotechnology. Reducing the risk of economic losses for local and regional authorities and fish farmers could become easier with the early warning system developed in the EnviGuard project. The team has traveled to Orkney Islands, Scotland to test their device designed to measure man-made chemical contaminants and biohazards in the seas and oceans. Monitoring the environmental quality would be beneficial to the European society and could improve food safety.
If you're going to put off a harvest, then you need to plan that because you've got people standing by, you've got customers waiting, but obviously you can't afford to put product on the market that's not safe. In fact, it's illegal to do so. The industry needs whatever tools it can get these decisions to be made actually on site and as quickly as possible in real time rather than waiting for samples to go off and then something coming back in a day or two. This can happen in a matter of hours, so it gives a lot more power to the user, really.
Gaining a wider knowledge of toxic algae is another aspect where the EnviGuard prototype could provide help in the marine environment. Having more information on what triggers algae blooms could help scientists to mitigate the effects. For this, the EnviGuard prototype can also provide combined datasets connected to an earlier developed system by EnviGuard partner HZG. The Ferry Box and the EnviGuard prototype would allow scientists to get a deeper understanding of the correlation between harmful algae blooms, toxin production, and classical abiotic and biotic parameters.
What we are measuring is water temperature, of course, salinity. We can measure turbidity, chlorophyll concentration. It's also sometimes important to see, for example, oxygen depletion caused by strong algae blooms. We're also measuring the pH. That's always connected to the algae blooms because the algae are consuming carbon dioxide, and then the carbon dioxide is the acid which produces then or increases the pH at that time. So that's this combination of physical parameters and biological parameters to have one complete data set.
The EnviGuard prototype consists of 3 different sensors. The algae unit, which detects harmful algae, the pathogen unit to detect E. coli and betanodovirus, and lastly the chemical unit to detect okadaic acid, saxitoxins, and PCBs. These data measurements are accumulated in the EnviGuard port, which sends the information to a server via internet and can be accessed by each user through a specifically designed web tool.
The main interface is a web interface, so you can access all the data all over the world. Just enter the address and enter your username and password, and then you have the screen where you can see all the measurement data. It's quite simple. If a parameter exceeds, you get an email or a WhatsApp message. For example, my pH value is exceeding, so I have to act something. I have to stop the pump, getting water from somewhere else, or add some solutions to make the water quality better.
The EnviGuard prototype has been created to provide upfront advice to local and regional authorities and research institutes, as well as to aquaculture farmers running aquaculture operations. Users of the EnviGuard prototype will be able to act upon and mediate a potential issue, such as a harmful algae bloom, toxins and pathogens, or other industrial pollutants.
For the first time, we'll be able to monitor in situ at a certain location different parameters all at the same time. But it's also modular, so also farmers could use it according to their liking, or environmental agencies that want to just see whether or not the quality of the water body that they are monitoring is good or not could use it in the field. It could be set up at site, it could be taken to a ship, and then you can measure once per hour or every 2 hours, depending on the analyte, the concentration of different pathogens, toxins, or toxic microalgae automatically, and that for a week non-stop.
The EnviGuard project team has organized several workshops to introduce the prototype to local experts and fish farmers. The feedback received indicated that the implementation of the EnviGuard sensor technology will significantly contribute to a sustainably thriving maritime economy and to a maximization of the impact of research and innovation on European society and economy.
Obviously an awful lot of potential nasties out there, which we would like to be able to pick up, and to be able to do that in sort of near real time rather than the kind of lags you get at the moment would be really brilliant. I think it could be a game changer, and certainly for an area like this, which is so dependent on the quality of its marine products, the quality of its seafood, I think to have systems like this deployable and in place really would be a huge benefit.
The testing period of the first EnviGuard prototype has been completed, and the team has formulated a plan for the further developments of the system. The next steps will include the miniaturization of the machine, solving the problems occurred at the first testing period, as well as combining the hardware and software of the system. The 5-year EnviGuard project has shown the potential for early warning systems and the development of state-of-the-art sensors in the commercial aquaculture industry.
field of the environmental monitoring or measurement.
Thank you, Damash. Welcome everybody to the workshop for EnviGuard here. Just finished to say. I'm going to be an introduction project, and I'm personally working as a scientific coordinator of the project together with other colleagues from Aquabiotech. And I want just to give you an overview of the project itself. The TAPAS is the acronym for Tools for Assessment and Planning of Aquaculture Sustainability. And as the acronym itself says, the whole project is actually focusing on providing sustainable tools for aquaculture activities in Europe. And specifically is going to be focusing on both freshwater and marine aquaculture system. The project itself started in spring 2016 and is going to end in spring 2020. So it's a 4-year Horizon 2020 project. The main aims of the project is decrease the licensing time for the new and existing developments through providing research data that can actually help and with the good practices to incentive and make the good practices spread across everywhere so that people can actually get and decrease the licensing time needed for opening new aquaculture facilities or for upgrading and expanding the existing one. Enhance the public image of aquaculture, because there have been a lot of controversy due to some of the negative effects that aquaculture has on the environment, and also improving, as we said, overall the sustainability of the aquaculture operation in Europe. And this, again, is going to be achieved to providing research data for consolidating which are the, let's say, sustainable activities that can help preserving the environment where the aquaculture farms are created. The TAPAS project is implemented through a series of parallel case studies throughout Europe. As you can see from the map here, there are partners in Northern Europe, but also partners that are present in the Mediterranean basin, and also partners that are inland, because, as I said at the beginning, the TAPAS project is focused both on marine and freshwater aquaculture systems. And particularly, one of the other systems that is going to be included in the case studies is the assessment of using IMTA, or integrated multi-trophic aquaculture, as one way to expand and use bioremediation or biomitigation activities that can help improve the effects of aquaculture on the environment. In particular, the case study in Malta is carried out by Aquabiotech group as one of the partners in the project, and is focusing on the assessment of nutrients dispersion and retention of fish farm effluent, and the assessment of the better site and the feasibility of integrated multi-trophic aquaculture system in the Mediterranean. In fact, as you can see from basically on the map, and being most of you already Malta knows where we are in the center of the Mediterranean as a strategic location for testing the feasibility of the use of IMTA in this specific type of environment. And thankfully, we had, as Aquabiotech, a collaboration with one of the fish farm, MFF, in Malta, that is located in the southeast part of the island, as located here. And this fish farm allowed us to collaborate with them in order to experiment a trial for IMTA system. In order to start this, to organize the work related to this case study, the case study itself has been structured in a first stage that is a more explorative stage, because we didn't have any information. There was no information available when we started about the hydrographic characteristics of the bay itself, where the fish farm, that you can see the boundaries highlighted in red here, is present. So we needed to collect information that then can help us choose the best site possible for the installment of the IMTA system. So what we did, we start planning collection of hydrographic data using a current profiler. The current profiler is this instrument, black instrument here, located within a tripod K structure that then is deployed in the water and help us collecting information that then can be modeled in order to foresee the distribution or the main pattern of distribution of the nutrient within the water around. So we needed to collect information that then can help us choose the best site possible for the installment of the IMTA. What I'm talking about. So what we did, we started planning. This was the day that we deployed the instrument first. Hydrographic data using the current April current profiler. As you can see, some of the Aquabiotech are carrying out the instrument and trying to find the most suitable location for information that then can be modeled in order to the same location for a month at the seed. So every month the instrument records the data, and then within the water around to collect information and then deploy the different locations. We did this site possible what I'm talking about. So what we did many more. So this was the day that we of course, mapping data of the location where we were intending to use then the IMTA. And this helped us basically better understand which were the main currents and especially the main patterns of distribution of the nutrients around the area where the fish farm is located. So in this map you can see the first location where the current profiler was deployed, and then all the other location around the fish farm boundaries that is represented here. The map is updated to October, but then currently in November we already moved the instrument down here. And so the instrument is going to be basically moved again over and over for the whole duration of the experiment. That is going to be for the next year, roughly. So we are going to collect a good amount of data. The other information that we needed in order to figure it out, which was the best location for start our MTA trial, was information related to the biotic component of the surrounding area to the fish farm. So what we did was collecting the distribution information related to the distribution of Posidonia oceanica, that is basically the main marine plant that is present in the Mediterranean, and then provides one of the most important habitat in terms of production and productivity and biodiversity in the Mediterranean around the fish farm cages. So in order to do that, we used remote sensing survey that allowed to create this map. This map then was further verified through ground truthing. We use the ROV that we have here at Aquabiotech. And as you can see, around the fish farm itself, the distribution of Posidonia oceanica is really, really patchy or almost non-existent because of the perturbance of the water column clarity and visibility due to the presence of nutrients that are due to the aquafarming productivity. So this helps also to understand how the environment surrounding the fish farm is actually impacted and how far the effect of the nutrient dispersion is impacting the marine environment. So the other information then that we collected was through the collection of suspended sediments, invertebrate sample, sediment from the bottom of the sea, farm fish and fish feeds that were used to feed obviously the fish inside the fish farm, because all this then was analyzed using stable isotopes analysis in order to figure it out how the nutrients were uptaken by the food web present around the fish farm itself. The second stage of our case study, really was focused on trying to design the best possible way the system that could be used for bioremediation purposes within and surrounding the fish farm. And I don't know if you, if I just want to give you a very, very quick information related to IMTA system. Since fish farm are basically inputting a lot of nutrients through the fish feces and the waste of the fish feed that then turns in particular organic matter that then deposited on the bottom of the sea. If we can uptake part of this excess nutrient that is obviously having a deleterious effect as pollutants around in the fish water, we can use organisms like, for example, sea cucumbers that are deposit feeders, basically are eating the sediment at the bottom of the sea, and then making through the digestion and egestion these nutrients available back again into the water column, and they might be uptaken by the surrounding environment and made available to increase even the productivity. So if you remember what we have been looking at, the Posidonia oceanica distribution, the presence of an IMTA system could actually contribute on increasing the productivity of Posidonia and hence restoring the environment that has been partly disrupted by the fish farm activity itself. So in order to do that, the first thing that we needed to do was choose the right candidate for this IMTA system. And after long discussions and research, we found out that the Holoturia poli, as a sea cucumber, is one of the best candidates possible because it's a local species, is very tolerant for high temperature conditions, and can actually be found very easily around the surrounding waters in Malta. So in this case, we are going to deploy, we're going to use this organism for the IMTA trial, and the experiment started in October 2018 and is going to run until September 2019. In terms of experimental design, being this the fish farm, we are going to deploy basically 3 replicate cages that have been specifically designed for this type of experiment at 0 meter, so basically just underneath the fish farm cages, at 10 meters from the fish farm and 25 meters from the fish farm, in order to see how the dispersion of nutrients can actually affect the productivity of our sea cucumbers. The sea cucumbers is going to be considered within the IMTA model the extractive species, so the species that can help us do the bioremediation, uptaking all the excess nutrients. And again, here I can give you a practical video that shows you exactly what part of our work entails. So when we deployed, this video was taken when we deployed the sea cucumbers into the cages that were already laid out on the bottom of the sea. And so basically the divers have to go down and place in each one of the cages that has been labeled accordingly, obviously, to our experimental design, the sea cucumbers. The sea cucumbers have been chosen a very small size, around 30 grams each, so that then it's going to be easy throughout the whole year to follow one biometric measurement that is very, very important, the weight. So it's exactly like we would do for ourselves if we want to check if we are eating well, we are eating properly, and actually we are uptaking part of the sediment. We are going to weigh the sea cucumbers. So that's one of the important factors. So that's why we choose them so small, that then so can we follow them up their growth. So as you can see now, the diver, okay, there is a little bit of slowness into the showing on the video, but basically the diver is going to place 10 sea cucumbers in each of the cage, and then the door of the cage is going to be closed with one of the cable tie. Every month we go down, we open the cages, we collect the sea cucumbers, bring back on the boat, weigh them individually, and keep monitoring their growth. So this is one part of our monthly study. After 3 months, we are going to collect some sea cucumbers from each one of the cage, actually two of them, and also we are going to use stable isotopes analysis in order to check from their muscle tissue if the sea cucumbers have been actually actively uptaking those nutrients coming from the sea cages to produce a biomass. So basically we are trying to estimate the percentage of these nutrients that are really becoming part of the sea cucumber's biomass. So now you see that the sea cucumbers are nice and snug into the cage. So every month, apart from checking the body weight of the sea cucumbers, what we are going to do for each of the experimental sites, we are going to check other other parameters like water temperature, dissolved oxygen, salinity, pH, ammonia, and so on and so forth, because these are going to be extremely important also to see how the surrounding environment is changing throughout the whole year of our experiment. Also, the sediment quality, where the sea cucumbers basically are around the area where the sea cucumbers are. So we're going to check the organic matter, the total organic carbon present, and so on, both on core samples collected from the bottom of the sea and the sediment traps. As I was saying just a few minutes ago, also the sea cucumbers are going to be analyzed for the stable isotopes of carbon and nitrogen in order to check which is the percentage of their diet that comes exactly from the nutrients, excess nutrients produced by the fish farm activity. And this overall should allow us to see how efficient the IMTA system it is and useful could be actually as a bioremediating measures towards the pollutants created by the aqua farming activities. In terms of future results, we are gonna basically look next year into the analysis for the stable isotopes and also follow up the growth of the sea cucumbers and the development of the other, their development within the IMTA cage. So thanks for your attention. If you have any questions. Yes.
I do have two.
Sure.
So the other day someone asked me, so you have a cage deployed near the sediment for the sea cucumbers, right?
What we have monthly deployment, we have what they call sediment trap. So we have two types of sediments that we collect.
Sorry. So when you put the cage, you put it on the sediment.
Yes.
But you kind of conceal the cage with the sediment. So the sea cucumber is going to be in contact directly with the sand.
Yeah. The way that the cage has been designed, the bottom of the cage itself, rather than have a rigid mesh underneath, as the bottom of the cage is made with a soft mesh cloth, if you like, so that actually adapts to the bottom of the sediment very well. And when we placed originally the cage there, we actually make sure that it was very well in contact with the sediment on the bottom. Obviously, every time we go there for weighing the animals or checking the cages itself, we always have like a look at how things are going and then if there needs any further adjustments or not.
Okay. Now I have another question.
Sure.
So why don't you measure the sea cucumber underwater? Why there's the need to come up and measure it on the boat? There's a difference? I don't really know.
I think the measuring the weight underwater, even if you had a very accurate balance of
because you also measure weight.
Weight, yes.
Only weight.
Only weight.
Not length.
Not length.
Okay.
Because the sea cucumbers as a structure, it would be very difficult to give a standard length because they are very, let's say, expandable in a sense. They are quite flexible, so their length really changes a lot. If it was a sea urchin or mussel, it would be easier in a way, but weight is actually the measure that we keep it for size.
Okay.
What is the depth of that?
Between 8 and 10 meters. Throughout the whole experimental site and also the reference sites is between 8 and 10 meters max. Yep.
Now, how did you measure and detect the nutrient levels? What did you use for that?
For the nutrients level, we use chemical parameters throughout the water column. As I said, we go monthly and we check nitrogen, ammonia. Instead, the nutrients within the sea cucumbers, we stable isotopes analysis.
Okay. And then you do stable isotope analysis?
On the sea cucumbers.
Okay. You kill it?
You? Yes.
You kill the whole? Okay.
Yes.
And then you use like a mass spectrometer or what?
For the stable isotopes analysis, no, you use basically an IRMS That's because what happens is that the samples get burned, and then the gas are measured in terms of carbon.
Gas
spectrometer, yes, rather than mass spectrometer, yes, correct.
Okay, if there is no further questions, I would like to ask Ines to have her next presentation about a specific project, which is not a Horizon 2020 project. It's a kind of, it's called SmartAqua program, where the background of the program is that this is financed from the national budget of the countries participating in the SmartAqua program. And since Malta, the maritime industry is an important industry, Malta is participating in the program and provide us a budget for the research in this project. Why is this impaired? Okay, just maybe if you use the okay.
Okay. So hello again. So I'm going to speak to you a little bit about the SmartAqua project that we have currently at Aquabiotech. We are very excited to start with this project. And its connection to the monitoring corrosion in the marine environment. Okay, so what is corrosion? Corrosion is a thermodynamic process that occurs due to the interaction of active metal alloys with the surrounding environment that leads eventually to the degradation of metallic structures. Corrosion is actually the cause of environmental economic problem worldwide, and it represents more than 3% of the world's GDP. And it costs around $50 to $8 billion every year to the industry sector. Corrosion is relevant in offshore structures like, for example, oil platforms and windmills. Why? Because they are under aggressive conditions such as high salinity and humidity. So why detect and monitoring corrosion? Why is this important? Why does it make sense to do this? Why? So we can extend the service life of offshore structures. We can reduce the life costs of these structures. And if we detect at an early stage corrosion, it can save around 30% of the ownership costs. This corrosion detection system should comply with several parameters, like, for example, detection of corrosion on set in any location. They should have a rapid response. They should be sensitive to detect and measure minor changes in the corrosion rate of the structure, and should be cost effective. And to have a continuous monitoring, they should be cost effective. Preferred characteristics of a corrosion detection system are in situ and non-destructive nature for the monitoring of the corrosion, and protection of the surface against external challenges. So current methodology that we have right now to measure corrosion. So we have acoustic emission and ultrasonic methods, something like optical fibers, we all know them. So they have been around for quite some time. Thermal imaging and electrochemical sensors. The choice for the inspection methods depends, of course, in the cost versus quality. So for example, visual inspection of a metal structure, it's cheap, but it's not always the best one because we need to remove fouling, for example, from these structures. By the time that we remove all the fouling, our structure will be more corroded. So medium cost techniques, we have ultrasonic magnetic particles, eddy current leak testing. They are very expensive. X-ray ultrasonic devices, they are even more expensive than the others before. So what do we really need? We don't want complex and expensive equipment that cannot provide us full information. So we do need non-destructive ways to monitor this corrosion. However, these non-destructive ways they are not always straightforward. Like, for example, the squid sensors. They are capable of measuring a flux of the magnetic field of a structure, but then we lose a lot of time letting the equipment cooling down. It's not viable. So we have some destructive ways of measuring corrosion, like I said before, measuring the magnetic field that results from the presence of electrical corrosion currents, or using MFL, that is the magnetic flux leakage, that measures and quantifies the corrosion through an application of a local magnetic field. These methods are already being used in large-scale metallic structures and pipes, aircraft parts in water and sodium solutions, and some steel structures as well in the marine environment. So what do we actually need to detect corrosion that it's cheap and eco-friendly and everything? So we need a low-cost, eco-friendly, efficient solution to monitor corrosion. Why? Because earlier detection leads to earlier repair of structures, meaning that the structure will not fail, nothing will collapse. It will prevent, for example, oil spillage from oil industry, though protecting the environment and economic losses from part of the industry. We will also have low costs in maintenance and related activities, like both costs repairing the structure itself, and by diminishing the transport, we also diminish greenhouse gas emissions. So SmartAqua, what is SmartAqua aims to develop? So SmartAqua aims at developing a sensing strategy to detect in a cost-effective manner the degradation of metallic structures. How? So we will have over our steel structure, we will have a nanolayer that will have essentially two parts. So we will have a splash zone and a zone underwater. Our splash zone will have a nanolayer that has colorimetric detection. So it's simple, it's user-friendly, and is reliable in detection corrosion on splash zone. So for example, we are observing corrosion. So the color of our nanolayer will change from, example, gray to pink. Underwater, we will measure magnetic fields. So if we have corrosion, this will give us an indication of, like I said before, fluxes of magnetic currents that we'll be able to measure with magnetic sensors. So the concept of SmartAqua is to modify conventional paint systems with an environmental friendly functional nanolayer. SmartAqua also addresses 4 major European sociality challenges. Transport industry. Why? Because it develops a set of eco-friendly solutions for the early detection of corrosion based on nanotechnology. Second, food security, agriculture, marine inland research, and bioeconomics. Why? Because it promotes the marine corrosion and marine ecotoxicology research and develops an eco-friendly, again, and safer by design products. 3, climate action, environment, resources efficiency, and raw materials, because it assesses the environmental impact of the SmartAqua systems that contribute to a low-carbon, eco-friendly, and sustainable aquaculture economy. 4, Europe in a changing world. Why? Because we are 3 partners. One is a small, medium enterprise, that is Aquabiotech. Another one is a university, University of Aveiro. And another one is a research institute, SINTEF in Norway. So the SmartAqua project. SmartAqua project has 7 work packages. The University of Aveiro is responsible of coordinating and managing the project. And SINTEF, our Norwegian partner, is in charge of dissemination and exploitation. Aveiro is also involved in work package 2, you can see there in the corner, that is synthesis and phosphorylation of sensing additives. So they will synthesize the nanocontainers that will then be used in the nano layer. They will synthesize magnetic nanoparticles and then release studies with, for example, methods like HPLC. So work package 3, it's led by SynTef, and they will formulate the nano layers. They will test dispersion stability, viscoelasticity properties, curing in thermal stability, leaching studies, and hardness and context of the nano layer. For work package 5, Aveiro, the University of Aveiro are the leaders. What will they do? They will test the electrochemical and magnetic characterization of the nanolayer by magnetometry, for example. Regarding work package 5 and work package 6, Aquabiotech are the leaders, but SynTef and Aveiro are also helping. So what will we do? We will assess in work package 5 the exposure of our nanocontainers and our active compounds in species that we already know, so algae, artemia, mussels. And then we will take these nanolayer to the field to do real tests. So the Aquabiotech role in SmartAqua. For the exposure assessment, so we will test. So Aveiro was responsible for, the University of Aveiro was responsible for testing each one of the active compounds that are going to be included in the nanolayer and the nanocontainers itself individually. And Aquabiotech is going to test the water that comes from the nanolayer. So the nanolayer will be putting it into a tank, and then we will leave these nanolayer to lixiviate into the water, and we will test this water in different time points to see what is the toxicity of the water providing from the leaching from the nanolayer. We will test these the nanomaterials, the active compounds, the systems, and the nanolayer itself with trichornotone, that it's attaches to the surfaces. So we will test the growth inhibition of the algae, and then Begula, that is a bryozoan or a mussel. Then we will take the nanolayer to the field, and we will test it using metal structure. So we will test the final nanolayer in splash zones because we have an offshore site. Aquabiotech has an offshore site. So we will test the splash zone, the fouling, the changes in color in the splash zone, and then underwater. Aquabiotech is also responsible for the exploitation plan. We will upskill and give prices and technical implementation aspects regarding the project. We will see why is industrial relevant, the results that we will obtain, and what is the relevance of the risks and innovative technologies or products that we are going to have. So that was it for me. Any questions?
Questions about the SmartAqua project?
I want nanoparticles that are signaling that there's corrosion. You would still need to go there and do a visual inspection of the areas. So you're not really eliminating the visual inspection part, or how does this work?
No, you are not limiting. Well, first you have to test. So you have to see, and you have to go and check visually for a while. Mm-hmm. But imagine that you don't have results in the first week. That means something. Maybe you don't have to go in a month's time. You know, it have to be assessed.
It's an easier way, so it's facilitating the visual inspection.
Yes. So, for example, if the splash zone part of the actual structure, that the splash zone, if it changes from one color to the other, you might think, okay, this is starting to corrode, so we have something, so maybe we need to do something. Mm-hmm. You know what I mean? So if you, yeah, did I explain myself? Yeah. Okay.
I don't know anything about this. People who manage these things, for example, you've got a structure, they have people whose job it is to make sure things are structurally safe. I mean, surely in civil engineering and things like this, they tend to over-engineer things. So would it not be a case of they just have practices that make sure things happen before it becomes a problem anyway?
This would be an early warning. So in the splash zone, if you see a change of color,
Yeah.
you can, okay, maybe something has happened with my structure. Maybe I'm going to take hands right now, I'm going to see what's going on, and I'm going to proceed with measuring magnetic fields in zones, for example, underwater. Maybe my structure is not only being corroded over the splash zone, it's also below. So you can change the structure immediately instead of waiting until everything collapses. And the costs will be much less.
Yeah, my kind of point was, but don't they just take preemptive action anyway as part of the management of the structure? Is it not just built into the management procedure of looking after what they've got so that they make sure things can't go wrong because they preempt things and do things prematurely, for example?
I would guess so, yes. But this is going to be another way of helping them. Because,
to make things easier.
To make things easier. Because usually to look at a structure that is underwater, you need to remove fouling.
Yeah.
You need to invest in divers.
Yeah.
So if you have a change of coloring, for example, in the splash zone, okay, I will check the magnetic fluxes underwater. If they come out okay, I don't need to remove all of my fouling and replace the old structure. You know.
Okay. Yeah.
Any more question? If not, we can have a general discussion about the whole topic today in terms of the monitoring systems and measuring the impacts of the environment of the human activities and the impacts of the human activities on the environment. If you have any comment.
We received a question on live stream.
Okay.
The question is, do you have any project which focuses on measuring parasites?
Not at the moment. We don't have that project. We are just starting now a project, a new Horizon 2020 project called iFefficiency, which will have actually the kickoff meeting on next week. And in that project, we plan to develop a so-called iBoss system, which is a kind of online monitoring and fish behavior monitoring system, which will also deal with the parasite detection on the fish. Especially, it will focus on the detection of the sea lice on the salmon.
Interesting, because there could be many applications for that. It could be the old, when in the old days of mining, they would take a canary down the mine field. And if the canary is singing, it's great. If the canary is on its back with its legs in the air, so there are things in the ocean you can do to test, to predict what's going to happen next. You can use your other wildlife as detectors. One of them being phytoplankton, for example, measuring its fluorescence, which I don't think has been done, but it's interesting because that would be an indicator of general water quality around fish farms and around industrial areas and drinking water quality. When you go in the ocean, you put your hands in the water, you see all the shiny things, then you can use not too smart technology to be able to pick up the spectrum from that, and its incidence and its intensity, and it would be a really, really good indicator.
But the fluorescence you're talking about is just related ones.
Because it will be a good indicator of general water quality.
Chlorophyll, eh?
Yeah, you can use the same organisms that are in the water anyway. You get data out of them, especially the ones that are easy, like using photospectrometry or fluorescence.
When EnviGuard was deployed, there was also another piece of equipment called Ferry Box. And the Ferry Box would measure parameters like pH, oxygen, temperature, and also chlorophyll A. So
But that's a product already on the market, and
Yes,
the plan
yes.
was to integrate the EnviGuard sensors with this Ferry Box system. And that's an area where we still have to develop the EnviGuard sensors.
Do you know how they did it? How they went around?
No, this is an old project, I don't know. Do you
The
know,
ferry
Tamas?
box is actually mounted on ferries, that's why it's called ferry box.
On ferries?
Yeah, on commercial ferries that go across the whatever
Like-
area.
Makes sense. You
So
go
that
across.
you can
Like
They are
mobile-
taking the samples.
Anyways, I mean, they are running anyways every day, so then there is a kind of way of uploading data.
And they did phytoplankton?
The Ferry Box, no.
No? Okay.
It can be an interesting application here in Malta as well, because we have ferries going all the day between Gozo and Malta, and also it would be interesting to take samples from the Grand Harbour using the ferry between Birgu and Valletta, or
But even the one that goes to Sicily back and forth into the channel.
yeah.
It's cheap
Yeah,
technology.
because
And it's not,
they have to run anyways.
it's not something which is like out of this world, you know, just an application for old technology over something with perhaps a new idea. No. So there you go. We want money for that.
We plan to do more work in this sensor technology and monitoring technology. As I said, in this efficiency project, we just will start now. We also will test new monitoring methods and monitoring systems, but those will focus on the aquaculture management and how can we manage the aquaculture systems better.
But seriously, is it possible to obtain funding for this sort of thing?
Yeah, of course, that's as Franco mentioned in his presentation, that's one of the biggest problems now, that we have a lot of measurements on the environment, but this is very fragmented. Different universities does that, institutes, government organizations, and one of the main trend now in this area is not just developing new sensors. That's one issue, to develop the new sensors which can more easily measure things. But it's also an issue to collect this data in a cloud system and make it available for every stakeholders. And remove this fragmentation from the whole system.
For example, a unifying way of putting all this data together is one of the aim of the TAPAS project, because ultimately what they want to provide is a toolbox that at the end of the project, everyone that wants, for example, open a new aquaculture facility or whatever, can check in the system and see which areas.
That's available, which is
But also to see which part, for example, in the environment has still a carrying capacity to support yet another farm or not. And one of the aim is basically collecting data from every different sources that can map the European area and say, okay, but in order to do that, you need to collect data from different sources.
Which reminds me, you know, when we had the issue of pollution from fish farms here, if one of the things were floating albumin or floating protein and lipids, I was wondering if actually that's taken care of. How is it taken care of? How is it? What technology do they use for detecting that?
To monitor
There are various reasons for those two particular
But
things.
here in Malta?
Yeah, for protein and lipids in the water. But that's fairly, it can be automated. And, I mean,
I think they just let it float.
Pardon?
I think
Yeah,
they
but
just
it's a huge advantage to know when you're forming seasonal, effective amounts of pollutants.
It would be interesting in that sense that it is believed that this foaming process in the pollution from especially from the tuna farms, where they use the specific feed. It's not feed; it's raw fish. They provide raw fish for the fish, and the reason of the foam on the scene is the lipids and proteins from this. But it is believed that also algae contribute to this, because they continuously have this feeding method, but we don't have this foaming thing only in certain periods of the year and only in certain years. So scientists think that the foam will happen if an algae blooming and the pollution comes together, and that creates that foam and problem. So in that sense, to detect that algae which cause the foaming impact. That would be important. And maybe because the algae detection unit of the EnviGuard works well, and we can adapt it to other algae species as well. So it would be a possibility for the country. If you don't have any other comments, any comments on the web? Yeah?
So with regards to the EnviGuard,
yeah?
So how do you envisage that the sensors will be used with regards to fish farmers? Would it be the obligation of fish farmers to use this device, or would it be the authorities and the consultants who wish to monitor the environment area?
Yes, definitely the consultants and environmental authorities also a target group of this system. Fish farm was just, and the fish farmers were just a focused target group of the product, because we thought that they might be the best and most interested end users. But we also learned during the process and during the project that maybe the environmental authorities can be more interested in these results, especially because the recent prototype of the system is a land-based unit, if I am right. So it would be difficult to put it on a fish farm at the moment. But it's very good for it's very applicable for that, to have a fixed location somewhere on the shore and collect data close to the coastline and provide data for the environmental authorities, for example, about the quality of the water. So thank you for your participation in the workshop, and I hope it was useful for you. And I can promise you that we will organize similar workshops in the future about our work to give you an overview and give you an inner look what we are doing. Thank you.
Thank you.
Stop.